it's quick. My name is Deniz Özkundakci. I work for the Regional Council here in the Waikato region. My job title is Lake Scientist, and I really appreciate the opportunity today to give a presentation to you about a topic that has been on our radar for quite some time now, which is really understanding representative monitoring under the National Policy Statement for Freshwater Management, and hoping to be able to show you today that we can use satellite remote sensing to give us this better understanding. And this is research. I'll be applying a tool that has come out of this LEARNS research project, really, and I've been working closely with Matthew Allen on this. I'm afraid I'm going to have to give you a couple of dry legislative slides, really, to highlight to you why we are doing environmental monitoring. It's brief. So, principally, really, local government has environmental monitoring responsibilities that really come out of the Resource Management Act, formulated in '91. And while there are numerous objectives usually for designing and implementing monitoring plans, the Council is primarily interested in being able to understand or checking that we are on track for meeting our objectives. Obviously, we're also interested in being able to provide a good knowledge and information base to enable sound resource management decision should the respective decision maker decide to utilize that information base for decision making. Obviously, monitoring data can also have provide quite a lot more information and can tell us so much more about some of the pressures on the environment, can tell us about the condition or the state of those lake ecosystems, and also, if set up properly, can tell us about the trajectories of those lake ecosystems in terms of trends into the direction that we want those lakes to go. So the National Policy Statement for Freshwater Management was released in 2014 and amended in 2017. Stipulated very clear policies around developing freshwater and lake monitoring plans for regional councils to implement. And while some of these policies are still formulated at a reasonably high level, they have given us clear direction and mandate to really properly justify where, how, and when we monitor those ecosystems. And if you are interested, or if reading legislative documents pushes your buttons, please, this is worth a read, have a look at these policies. So quite a few questions arose from these policies for us to really get our heads into. And the biggest one of all is really what is representative in terms of monitoring, and how much information is enough for us to be able to say that we now have a representative picture of what's going on out there. A couple of more detailed questions that I've been getting stuck into is where do we gather those that information, and how often do we actually have to collect information to meet the representativeness? And I think the answer to those questions really is, the key to answering those questions is if we start taking into account management considerations and statistical considerations. And I'm going to focus a little bit more on the statistical side of things for today's talk. So if I had to categorize and very broadly categorize statistical considerations for determining monitoring requirements, I would probably come up with three broad categories here, one of which is that we have to accept a certain level of error in our measurements. So statistically speaking, that is because we cannot always monitor everything at the right time and in the right places, so we need to be able to understand what the error in our measurements is in our monitoring plan. The second point is really that we need to understand, and quite well understand, what the natural variability of those ecosystems are. And that's because lakes obviously respond on very different time scales to daily weather conditions or to broad-scale climatic conditions, to nutrient inputs, which render lake ecosystems very variable. So we need to understand that, and those 2 points obviously feed into something that we can calculate in terms of number of samples required to meet these representativeness goals. Visualization of those 3 big points in a graph could look like this, where you're looking at the y-axis representing the number of samples that you would have to take, The x-axis represents an indicator of variability. Here, the coefficient of variation with low values indicating that the lake isn't isn't very variable at all, and large values indicate that the lake is very variable over particular timescales of interest. And the accepted level of error is here displayed in these grey segments in the graph. So for the practical approach for water management has been traditionally, and probably rightfully so, to accept an error in your measurements around the 10 to 20% mark, which is probably a fairly well accepted sort of level of error to still enable sound decision making in terms of resource management. For us, it's also interesting to understand at which point we'd be probably overdoing some of the monitoring efforts in terms of we collecting so many samples that we're achieving a level of accuracy or precision in our data that is probably not necessary for still making good decisions. So we can probably use that money or that resource in other places to gather more information. The key in this graph is that the higher your accepted level of error, the less useful your data really becomes for making good decisions. And at some point, I would argue that you're entering an area of monitoring where it becomes a little bit pointless, and flipping a coin might be just as good in terms of making good decisions or poor decisions for that matter. Okay, with that information in mind, we can play a couple of games in this with mathematical equations. Let's say, for example, we're accepting an error rate of 20%, and we know that our system has a sort of moderate level of variability. We would have to take 62 samples to accurately assess the condition of that system, and over the course of a year, that would roughly equate to weekly monitoring of our system. The other way around, we could look at this, for example. We know that we're taking monthly samples over the course of a year in a system that has reasonably high variability. We can see that the error that we would have to accept is fairly high, at which point I would argue that we have to substantially review the monitoring network to enable good decision making. Right, so what's clear from these slides is that you need to understand your system fairly well to begin with to enable the development and implementation of good monitoring plans. That is a bit of a conundrum and very challenging in areas where your lake monitoring program is less developed and the data just doesn't exist to do the necessary calculations. This is where remote sensing comes in for us. That we've seen now in previous presentations can really gather information at national or regional scales. So for this talk, I'm not going too much into detail about the technology. So broadly, we've utilized NetSat 7 and 8 satellite images captured between 1999 and 2015 for 109 lakes in the region. We have roughly 200 lakes in the Waikato region. And we use total suspended solid concentrations that were derived from satellite imagery to carry out our analysis here. And I appreciate that this is not part of the National Objectives Framework, but it is an optical property of water that we can relatively easily detect with remote sensing. And we used that data set to calculate how many samples we would have to take in our lakes to enable a representative monitoring regime. So we did that in two different ways. Once we were interested in understanding how many samples we would have to take in a given lake over the course of a year. And the second approach was really we were interested in understanding how many samples do we have to take within a lake on any given occasion. And that's because we know that horizontal variability in those lakes can be quite substantial. And we wanted to understand how substantial that really is. Right, so this is an overview of the data set that we derived for 109 lakes. So you're looking at the x-axis here, which is total suspended sediment concentration in those lakes. Each of those blue bar plots represents a lake over the entire study period. And needless to say that the Waikato region has quite really turbid lakes with concentrations of up to 200 milligrams per liter here at times. I think the key message, what we got out of this, drilling down a little bit deeper into this data set, is that interannual variability was very high in those lakes, and that means that no 2 years were the same in terms of assessing the condition of those lakes. And we also learned that spatial variability was quite substantial in a lot of the lakes, larger lakes, and lake depth also influenced that spatial variability. Just in terms of the spatial map, what this could look like for determining the horizontal variability, So this is one of the lakes that we call in the database LID 50782, or Lake Waikare for some people who live in the Waikato region. So the turbidity method you see derived from the satellite remote sensing image sort of highlights to you that the horizontal variation can span an order of magnitude in terms of concentration on a given day. And I've put beside that a photograph taken from a chopper only a year later, because we don't really line up our chopper flights with satellite image capturing. But just to give you an idea that those sort of horizontal variations are real, and they usually happen often after big storm flow events when a lot of sediment is transported into the lake. So it's pretty clear that if you took a single sample from a single station in this lake, you might not capture really the true condition of that lake. Okay, so how many samples do we actually now need to take in these lakes? And instead of showing you the results for 109 lakes, I attempted to synthesize the entire data set into two graphs here. And what we're looking at here is the cumulative frequency distribution of the number of required samples per year in any given lake against the percent of lakes across all years where we would need that the accepted level of error of 20%. Hope that makes sense. What I think is clear, and hopefully for you too from this graph, is that monthly monitoring, indicated here as the blue line, so that's 12 samples per year, would only really give us a good estimate or a good understanding of the condition of the lake for 33% of the time. That's not very much actually. So 66% of the time we would probably misrepresent substantially the condition of those lakes. If we increase that frequency to weekly samples, we suddenly start to capture 88% of all the lakes all the time in terms of precision for determining the condition of those lakes. And the true answer for implementing this practically is probably somewhere in the middle between monthly and weekly sampling. In terms of spatial variability, okay, so this is quite scary. The number of required samples goes up really quickly in a lot of those lakes. What is clear for me in this graph is that a single sample from a single station is never enough in any lake, and we need to now start sort of re-evaluating the way we do some of the monitoring on our lakes. And I think a practical solution could be that we start collecting water samples from multiple sites for any given day and then pull them into a big bucket or something for analysis. We're still working on some of this. Which brings me to my last slide, really. Okay, so hopefully I've given you a brief overview of what remote sensing can do in terms of generating large data sets. I think they're great for assessing the condition of the lake, but I also think there's huge potential to take that further, to think later on about some of these large data sets to inform the development of monitoring plans. Obviously, we're going to discuss the results in the lake's resilience framework, because I think their ability has something to offer to interpret resilience indicators in lakes. And if you're interested in a larger project around designing monitoring programs at a regional scale, please talk to me maybe after this talk. We are in the process of carrying out a couple of more analyses, and we're also in the middle of the process of developing an unbiased, spatially balanced representative monitoring network, which will answer the questions of how many lakes and which ones do we actually pick from the regional lake set. Thank you very much for that.